Right, welcome back everybody. In this video we are going to discuss concepts related to section 6.11 of AP Calculus BC. This is our first BC exclusive topic, integrating using integration by parts. And I've broken this concept down into two different lessons, and each lesson is probably going to be broken down into two videos, depending on how things go. But that's kind of the game plan. So we're going to start here in our first video using integration by parts part 1 by introducing you to the basics of the concept of integration by parts. And then we are going to work our way through some examples of a couple of different integration by parts techniques. Okay, this technique's called integration by parts because basically what we're going to do is we're going to split the integral that we're attempting to find into two different parts. And this technique is used when we have the product of two different types of functions. Like maybe we'll have a polynomial type function times an exponential type function. Integration by parts can help. Or we could have a logarithmic based type function and a polynomial type function. Integration by parts can help. In fact, integration by parts is even the technique that we use to integrate some fairly simple integrands that we've been unable to integrate up to this point, integrands related to natural logarithm functions or, any kind of logarithm functions, and inverse trig functions. Those are things that up until now we have been unable to integrate, but using the technique of integration by parts, we will be able to. Okay, so where does the pattern for integration by parts come from? Basically, it's important that you understand that this comes from the product rule. When we take the derivative of u times v, the result is equal to u dv plus v du. Okay? Now, if we integrate this expression, the integral of the derivative of u times v gives me just u times v, and when I integrate the right-hand side, I can split it up into each of these individual integrals, the integral of u dv plus the integral of v du. So all we've done to get this template that we're going to use for integration by parts is take the integral of the product rule. So if you ever forget your integration by parts setup, you can kind of develop it from there. If you know the product rule, you can take the integral of both sides of the product rule, get to here, and then subtract one of these integrals, and we end up with this expression, that the integral of u dv is equal to uv minus the integral of v du. That is the key setup for us when we're using integration by parts. Okay, using this we can set, I already mentioned that. One of the first tasks we're going to have to do is we're going to have to find and figure out for our particular integral which function is best as u and which is best as dv. And what I'm about to say is not going to mean a whole lot to you right now. But once we know what our u and our dv are, we're going to differentiate our function that we have for u and integrate our function that we have for dv, which will enable us to find functions representing du and v. Once we have all four of those things, u, dv, v, and du, we can substitute them into this integration by parts pattern and go to work. Okay? Now, if it were me and I were sitting there right now, the next question I have might be, well, if we've got things being multiplied, how do we decide what to use as u and what to use as dv? I use what's known as the LIPET rule. I've seen a lot of people, in fact, more commonly lately, I've seen other people use the acronym LIATE to talk about which one goes first. But these are, in essence, pretty much the same idea. The thing is down in the bottom, with the T and the E, notice the order's switched in these. The Li is the same from one to the other. The A and the P mean the same thing. This is polynomial. This stands for algebraic. We're talking about the same functions there. But really, with the T and the E, those are interchangeable, the order that we pick them. And so the problems when we have like both an E and a T type can get a little bit messy. Alright, so anyway, this rule tells us which part of the integral is best to pick as your u. So L, those are logarithmic functions. If a logarithmic function appears in an integration by parts, it should be chosen as the u. okay, then I, inverse trigonometric. So if we have an inverse trigonometric, that should be our u, unless we also have a logarithmic. And we go down this hierarchy: polynomial, exponential, trigonometric. And we're going to frequently refer to this kind of hierarchy as we do these different problems, and we get into problems involving integration by parts. Okay. The first technique, and we're going to learn 4 different techniques for integration by parts. The first technique is what I call simple integration by parts. Simple integration by parts is one of these scenarios. It's when I have a first-degree polynomial paired with any of the other function types, or if I have a logarithmic function by itself, or if I have an inverse trigonometric function by itself. In all of these scenarios, we're going to use the basic technique number 1, what we call simple integration by parts. Here's how that technique works. We're going to identify our u and our dv. We're going to find the corresponding du and v. We're going to substitute these pieces into our basic template. And then this integral right here should be something that we can integrate using some previously learned technique of integration: substitution, basic straight antiderivatives, etc., etc. But in simple integration by parts, we should end up with a result like this. All right. Example 1, find the integral of x cosine of x dx. Here we have a first-degree polynomial and a trig function, which is an indicator to me that this is going to be a simple integration by parts. I think about my LIPET structure. In this, I have a polynomial function and a trigonometric function. So the polynomial function is going to be my choice for u. And I'm going to write those, just like I did when I did substitution. I'm going to write my u and my dv off over here to the right-hand side. So u is going to be the polynomial. dv is going to be everything else. And now I'm going to build the analogs of these. I'm going to take the derivative of u to get du, and I'm going to take the integral of dv to get v, and the integral of cosine of x dx is just sine of x. And now that I have all of these things, realize that what I've got going on here is this is my u, this is my dv. So what I'm looking at is I'm looking at the integral of u dv. That's equal to u times v. So I take u times v minus the integral of v du. The integral of v du. All right, and there's my integration by parts setup. And now I'm going to go ahead, and this part I can integrate on its own. The integral of sine of x is negative cosine of x plus c. And so this ends up being x sine of x plus cosine of x plus c. All right, now that we got the basic idea, we're going to fire through a few more examples. Example 2, find the integral of the quantity 2x plus 3 times e to the x. Again, LIPET, we have a polynomial and an exponential. So we're going to choose the polynomial as our u, and our dv is going to be the e to the x dx. I find the derivative of u. I find the integral of v. And then I set this up. The integral of u dv is equal to uv minus the integral of v du. And in this case, the integral of 2e to the x is just 2e to the x plus our constant. And this one, I'm going to actually simplify a little bit because I can distribute the e to the x through the parentheses here and combine some like terms. And there's our integral in example 2. Example 3. Find the integral of x natural logarithm of x dx. So here we're using LIPET again. Oh, logarithm, that's going to be my u. So u is going to be the natural log of x, because I've got an L and a P in this problem. And then dv is equal to x dx. I take the derivative of u. I take the integral of dv. Alright, and then the integral of u dv is going to be equal to uv minus the integral of v du. Now what I'm going to do before I integrate this is I'm going to go ahead and simplify. I'm going to bring the constant 1/2 out in front, and then x squared times 1 over x is just x. And so now I integrate that expression. The integral of x is 1/2 x squared plus my constant. And so this is 1/2 x squared log of x minus 1/4 x squared plus a constant. And there's my integral in example 3. Example 4. The integral of the base 5 logarithm of x dx. This is one of those I was talking about where we just have the single logarithmic expression in here. We'll handle this using integration by parts. U equals the base 5 log of x. dv equals dx. I take the derivative of this. This is going to be 1 over x natural log of 5. I take the integral of this. That's going to be x. And so now my integral of u dv is going to be uv minus the integral of v du which is equivalent to those x's cancel out, and I just have a constant in here. So when I take the integral of this, it just ends up being 1 over the natural log of 5 times x plus c. I actually can split this up using the change of base theorem into this, and I could simplify this out to a single term like so. Alright, last one. The integral of the arctangent. So u is arctangent of x because this is an inverse trig. dv is equal to dx. du is 1 over 1 plus x squared dx. v is equal to x. And so this is going to be uv minus the integral of v du. And here I'm going to use a substitution. I'll use t. T equals 1 plus x squared. So dt is equal to 2x dx. So 1/2 dt is equal to x dx. And so this becomes the integral of 1/2 times the integral of dt over t, which is going to be a natural logarithm. And so that's going to be x arctangent of x minus 1/2 natural log of the absolute value of t plus c. And then we bring t back. And since the quantity 1 plus x squared can never be negative, I don't need my absolute value signs. And there's my integral. So that was simple integration by parts. In the next video, we're going to come back and look at technique number 2 here, which you see peeking in the bottom of our screen, multi-step integration by parts. Until then, have a great rest of your day, and we'll see you in the next video. Bye-bye.